All right, so last time we talked about this logistic function. And one thing that I wanted to mention is that in a linear regression, right, the way that we get estimates of the beta is to minimize the sum of the squared error terms, right? In a logistic regression, the way that you calculate the betas is slightly different. This is kind of what happens behind the scenes when you run the GLM function and you have the family equals binomial. But I will kind of write this down here as a reference for you. So there's something known as, oh, all right, use a different marker. Let's see if this works. Great. A log likelihood function. And this describes the plausibility of a model parameter value given specific observed data. So this might look something like this. The log of P of xi plus 1 minus yi times the log of 1 minus p I. So each of the outcomes basically get logged times your y's. And this will end up looking something like this. So the way this works, the way that you solve for this is you set partial derivative equal to 0. So this would be and approximates numerically. Okay, so if you remember, for the linear regression, we can solve for our betas analytically, even though it's an optimization, because it's a solved optimization. So if you remember, it's something like beta equals x t x inverse times oh my gosh, I'm totally blanking. Is it y tx? Something like this. So you can't do that here, unfortunately. With the log likelihood function, this type of thing does not have a closed analytical solution. And so oftentimes what you'll see is when you run this type of thing in R, it'll have this thing where it'll say like iterations, blah, blah, blah. And what's happening there behind the scenes is it is solving for this log likelihood function. And it's doing this numerical approximation, and it sort of iterates through until it basically solves for your betas being equal to 0 for the log likelihood function. Okay, so that's kind of what's happening in the background. So now let's talk about multinomial logistic regression. Which is the next progression of stuff that we're talking about after our last class discussion about logistic regression. So this is a generalization of logistic regression to multi-class problems. Okay, so before we have something like binary outcome. And this might be something like f of k comma I, where this is our outcome and I is our observation. And that could be a function of some of your betas, right? So beta 0k plus beta 1k times x1 I, right? So for each type of outcome, you have a different set of betas, and this is specifically for your binary model, right? So last time we had this example of what was it, percent Democrats, and then Democrats win, and you only have here K only has 2 observations. But now we're going to talk about what happens when you have multiple outcomes. So same type of thing here. It's going to look the same. Ki equals beta 0k plus beta 1k times x1I. But now, now k can be greater than 2. So I talked about this idea that with the binary outcome, we have this result in our probability space that looks something like this, right? So this could be X and probability. And we know that, so if this is for P of 1, we know that there's a corresponding second one that looks like this, P of outcome 2, and the sum at any vertical line equals 1, right? The probability of this plus this, or here plus here, or here plus here should always equal 1. And that's kind of the guide for multiple outcomes. Let's say we have 3 possible things. You've got something like this, something like that, and then something like this. Same idea. You might extract just 2. You can interpolate the third one based off of the sum of these 2 plus the third one always has to be equal to 1. Okay. Any questions about this so far? So the inverse Logit term that we kind of worked with last time, for a binary, this basically looks something like the probability of a specific outcome, looks something like this, exp of beta x over 1 plus exp beta times x. And I'll show the generalized version. We're not going to kind of derive this, but just know that it looks something like this. Generalized. Okay, this is for your MNL. So probability of X, and let's say outcome C. So this is EXP Okay, and so basically the idea here is very sort of analogous to what's happening here. In the numerator, you're taking the exponent or exponentiation of your betas, beta c's, all the betas corresponding to that particular outcome times your x's. And then in the denominator, you're adding up basically this term for every other possible outcome. And that guarantees, right, that you have some kind of probability of this relative to all of your other sort of outcomes that are happening. Okay. Any questions? So let's take a look at implementing this in R. And kind of see what this looks like. Okay, let me share my screen. All right. Did I share the Disney Plus projects data from in the last lecture? Okay, so we're gonna load that right now, and that should be available on Canvas if you haven't gotten it already from the previous lecture. And let me load in a couple libraries. I'm not sure if all of these are actually needed. I should double check that, but that's what I have here. So we're going to load in ggplot, which we definitely need, nnet, which we'll definitely need, mass, which I think we'll need, and then definitely data table. Actually, yes, we'll use some of these after this demonstration. Okay, so go ahead and load in all of these libraries. Let me shrink this down a little bit so you can see. So I'm going to load in this data set here. Okay, so what is this data set? So we'll go ahead and click this. 7,850 observations. And this is a data set of Disney Plus movies and TV series. And what you can see from here is we have the title of the movie or series, the year in which it was either, is it available or released? I think it's released. The rating, so G, PG, PG-13, R, and then there's some TV ratings as well, like TV mature. The runtime, the genre, the rating, some number of votes corresponding to the rating, and then the director or star of that movie or TV show. Okay. So what I would like to do is see whether or not we can look at, well, let's look at this. I want to look at the relationship between the rating, which I think is called certificate in this data set, and the runtime or the length of the movie, and the rating. Okay. So we're only going to look at 3 of the outcomes. So let's plot this to see what it looks like. I'm going to look at, or sorry, 4 of the outcomes. The movie ratings, so this is a way that we'll sort of carve out all of the TV shows. There are a couple outliers. So I'm only going to include movies that are less than 200 minutes long, right? That's like almost 3.5 hours. And we're also only going to look at movies that have a rating greater than 3. So right now, what we're doing is we're just looking at the data to see kind of what this looks like. And I'm going to do a scatter plot with my x-axis being the runtime of the movie, the y-axis being the rating of the movie, and then the color color being the certificate. I guess I'm going to say certificate for R, PG-13, PG, and G as opposed to rating, because there's also a rating variable that we're using, which is something different, right? That's like its score. Okay. Oh, I see I'm using, okay, I think we're going to need another library here. R color brewer. Scale color brewer. Name equals movie rating. We'll do this just to be consistent. Okay. So let me go ahead and run this. Okay, so here we can see a sort of mapping of our movie certificates as a function of runtime and rating. And essentially what we want to try and do is be able to make some inferences about whether or not the movie certificate should be, G, PG, PG-13, or R, based off of these sort of 2 attributes. Okay. Oops, sorry. That is called R color brewer, and that I saw that I have this thing on line 14, scale color brewer. This gives, it's basically a more customizable set of like color palettes. And that's what I was using here. Okay. So let's create a new data table, which I'm going to call Disney filtered. And that's just going to be this guy here. I'm just going to copy and paste that from the ggplot. Great. We'll also notice that Disney filtered has quite a bit fewer number of observations. We went down from about 7,850 down to 722. Okay, so how do we run the model? So in this case, I'm going to use something called multinom in order to run a multinomial logit. And we're going to do certificate on runtime minute plus rating. Okay, so if I run this, we'll see some text pop up. Initial iteration, final value, and this is referring to what I was talking about before with the log likelihood function. It is doing some kind of iterative solving for an analytical solution. And then once it's converged, we are able to look at something like this. Okay, here. So you'll notice, as I was saying, we have a set of coefficients for each of our outcomes, PG, PG13, and R. And wait a minute, there's one more, right, which is G, but that is omitted because the combination of these guys will allow us to figure out what the sort of last one is. Okay. And so this is analogous to what I was showing last time. Okay, with the Logit model, we were looking at those coefficients. Okay, the only thing I can really tell you here is that as my runtime increases, actually across all of these, the probability that it's each of these will increase, which means that G is probably the one that goes down. But the extent to which that is happening is not something that I can just sort of tell you by looking at these coefficients. Okay, let me stop my screen share for a second. Okay, so I mentioned, so the probability of outcome XC is equal to EXP beta C X over sum K EXP beta KX. This probably looks a little cryptic, but let's say that I wanted to calculate the probability let's say that I want to understand what the probability that a movie would be PG-13 given a runtime of, let's say, 120 minutes with a rating of, say, 7. How would I calculate that manually? Any ideas? You look like you have an idea. Yes. Yep. Yep. Yeah, the same. Okay, yeah, exactly. I think you get the point. Okay, so just to kind of demonstrate, we did this manually last time for the sort of Democrat win example. It's the same idea here, right? What's happening is that I can take these values, plug them in here to make predictions about the probability. So in this case, you know, for a 120-minute movie and rating equals 7, then we say, let's say this is outcome C. So then I could say probability of this outcome C is equal to exp of this guy with those parameters, so -3.9 plus 0.0266 times 120 plus 0.2 times 7. And this is going to be all over this same thing. So it'll be exp of each of the things. It'll be exp of each of the things filled out for each of the choices, adding up, and this will give you the probability of that particular outcome. And that allows us to translate these coefficients back into the probability space that maybe we're sort of more familiar with. So let's see how we can do that. Go back to sharing screen. Okay. There is a package. Oh, I don't think I actually have that loaded here. Yep. 1 second. Yeah, it's called effects. Sorry, we have a lot of packages today. So reshape is just the package that lets us do like melting and casting. And effects is a special package that I'm going to be using in order to essentially do this prediction across ranges of values. So let's see what happens here. Rating, and then I'll fit. So basically, what this line of code is going to do is it says, I want you to vary the input variable rating. This is kind of like a predict function, essentially, across the sort of visible range of rating in the data. And then you're going to use the model MNL fit. So this gives something like this. Let's see what happens. Okay. So the one thing about this is that if I'm making a guess about the probability at a specific rating, in this case, we have two explanatory variables. So you'll see, right, in this equation, whatever outcome probability also depends not only on the rating here, but also on the runtime minutes. But we didn't specify anything about the runtime. We're only varying the rating. So what value is it choosing? So in this case, it's saying it's holding fixed the runtime value, and it just uses the sort of average. So this is saying, what is the sort of probability of a particular set, the probability of one of the outcomes, in this case for the G rating, as I go from a vote rating of 4 to 9, and you can see how this probability changes. And then it will also tell you for the PG outcome, as the rating goes up, it changes the probability like so. And so on and so forth for each of my different outcomes. So this is exactly the plot that I could draw to be analogous to that sort of S-shaped curve, but for all 4 sort of outcomes. And you can do the same thing for the runtime as well. So these 2 lines are kind of the crucial points that allow you to do the probability predictions for your multinomial logit outcomes. Okay. So let me graph these. So this part, you guys don't have to follow along. Again, you can look at the code later. There's a bit of work to translate lines 25 and 26. But the graphs that I'm going to show are essentially just doing that. I wrote a custom function to kind of extract this data here to allow me to plot it across a sort of longer range. Okay, so that is all this code here. And let me actually get rid of this and get rid of this guy. We don't need to save it. So again, don't worry about this code. You can look at this online later. And let's just look at the plots. Okay, I have to run this guy. Okay. So who can help me interpret this plot? Anyone? This is, right, the same thing that we had before with the Democrat win versus Democrat loss, except now we have more than 2 outcomes. Okay, so same type of thing. At any sort of vertical point, the sum of this plus this plus this plus this always has to be equal to 1. Okay, and this is basically telling me the probability that a specific outcome, and these are the outcomes are being my different certificates, G, PG, PG13, and R, are related to the rating, right? And so in this case, for the average movie length, as the rating goes up, it's more and more likely that the movie is either PG13 or R, and as the movie length, or yeah, and sorry, not movie length, as the range of ratings go up, and then as the range of ratings go down, then your probability for it being a G or PG movie decreases. I can't tell if y'all are real confused. Yeah.
And this is at the average runtime?
Yes, exactly. And we can look at the other one as well. So for the run varying across run times, looks something like this. So this one has a much stronger effect. So this 1, 2, 3, 4, 5 is just like I think it's the quantiles of runtime. But basically, the really big obvious one, right, is that as the movie gets longer and longer, it's much less likely to be a G-rated movie, and it's much more likely to be a PG-13 movie. So here we might say, oh, the signal appears to be a lot stronger for that kind of effect. And this is at the average runtime. Yep. No. For this graph, this is the average vote rating across a range of runtimes. For the other graph, it is a range of vote ratings for the average movie runtime. Yeah. So whatever this is here, the other variables are being held fixed. What would it mean to do a variation across both of them? You could actually do that in effects, but I don't know how you would graph it, right? This would be like a crazy, again, like some kind of crazy 3D plot. So even as soon as you get to 3 dimensions, like already, this starts to get a little bit tricky, but still, right, we're talking about, you're talking about looking at this type of plot versus the coefficients here, right? Like I don't know, again, like kind of what these mean relative to each other. Like to me, the context provided by the probability plots is way more useful generally, right? Like I can be pretty confident in saying something like, oh, the longer the movie is, the like less likely the movie is going to be rated G and the more likely it's going to be rated PG-13. And I can tell you relatively what that looks like, right? Okay, yes. Uh-huh. Yeah, whatever the average rating is, it just holds that fixed. So it's essentially what the effects package is doing is like this, okay? And what we're doing in this plot, range of runtimes. So this value here, I'm gonna do like 60 minutes, 75 minutes, 90 minutes, 105, whatever. I'm gonna vary this thing, the number of minutes, but I'm gonna hold this fixed. And this is being held fixed at some particular value, which is, I think, the average value of what you observe in the data. So note that if this value were altered, right? So let's say the average rating, vote rating is 7. That's giving me this plot. It's going to be the case that, let's say instead you chose to use the rating value of 6 instead of the average of 7, this plot will start to look different. Okay. I don't know exactly the extent to which it'll look different, but it changes kind of your like starting point, right? And so, yeah, that's one thing to keep in mind. Yes. Yeah. Yeah, because it's just grouped by quantiles. So this might correspond to like a 1 hour runtime, and then that might correspond to like a 3 hour runtime.
Could we change that to like minutes?
Yeah, you can. It's a little bit more work because the thing is the way that I wrote this function. So we did this whole thing about getting the effects, right? And it gives you the probabilities across some values of like ratings. The way that this function is written to translate from the effects, it takes the default settings so that it can be generic across anything that you put in. So that's why it's always 1 to 5, but you can customize it. Okay. So how good is this model? We are going to look at something. So we're gonna venture a little bit into the realm of what's more commonly done in like machine learning approaches, where they're concerned particularly with prediction. And so you may care actually a little bit less about, the idea of the trends that you're seeing from the probability plots. You just want to know the outcomes. So what does that look like? So what I'm going to do is feed in some values. So I'm creating this grid of basically a bunch of different possible movie runtimes versus vote ratings. And then I'm going to feed that into a predict function to look at all the sort of probabilities. And okay, so let's say I feed in an average value for rating and whatever this runtime would be for, which let's say that's like 3 hours or 2.5 hours. Okay, so I feed in 7 and 2.5 hours. So from a prediction standpoint, what do you guys think the model should tell me? Right here. Yeah, exactly. So purely predictively, I'm going to just say, well, I think I'm going to predict the highest likely outcome. So at this point, I'm just going to say that's PG-13. And if I predicted here, I'm going to say, oh, that's PG. And then if I predict over here, I would say, oh, that movie would be G. And in fact, in this particular case, at this particular vote, or sorry, at this fixed vote rating, you would never pick an R movie, okay, because of how this plot looks. Okay, so let's go ahead and do that. Okay, so here, all I'm doing is I'm taking my expanded grid thing, which gives me all the different combinations of runtime and rating values that I want to look at. And I'm feeding it into our predict function for the model that we had fit for the multinomial logistic. Okay, and then, typo. This second part, all I'm doing is making a factor here. Okay. Oops. Run that. And then let's look at a plot of what this predictions look like. So I'm going to have two sets of points here. The first set of points is going to be the predicted values across all these ranges of runtimes and ratings. This alpha 0.2 that I have here, that is a parameter that you can add into any of your geoms to make it transparent. So alpha equals 1 is the default value. It makes it totally solid. Alpha, the lower it goes, the closer you get to 0, the more transparent it becomes. So we'll see what that looks like in just a second. And on top of that, I'm going to plot our original data points. And we'll see what this looks like. PCH here is an indication for the shape of the point. This one, I'm making it so that it has an outline, and I'm making that outline black. And we'll see what that looks like in the plot in just a moment. That way I can distinguish between my predictions and my original. Oh. Okay, what happened? Comma, yes, thank you. More errors. Sorry, what was that? No, it's not. Thank you. Great. Okay. This is what our plot looks like. So each of these points here indicates that so each of the points that you can see with the sort of black outline, these are our original points, and everything sort of these triangle shapes that you see here with these clear boundaries, those are the predictions made by my multinomial logistic model. Okay, and this is typically kind of the visualization that you're going to see. It creates these sort of linear boundaries. That's why actually the sort of linear in parameters is leading to this kind of thing happening. And we can see, right, that these coverages aren't perfect. Okay, you're going to have some predictions that are incorrect, right? There are a bunch of, there's a lot more sort of heterogeneity even within, but the error rate here should, in theory, be sort of better than just guessing. Okay, and so how would we calculate something like an error rate here? What do you guys think? So there is this kind of nuance here, right? That like, for example, like maybe it's the case that like the probability in certain places for a particular outcome, maybe they're really close. It just happens that one is like slightly closer or slightly higher, and therefore it gets chosen. And that's why this is all blue. But that's not, that doesn't really help you with the error stuff, right? Like if you get it wrong, you get it wrong, right? So if I were to just like ask you guys what the error rate of our model would be. Exactly. So blue and blue, correct. Blue and blue, correct. Green and blue, wrong. Red and blue, wrong, so on and so forth, right? So I have some number of correct and some number of incorrect. And you can just say the error rate is equal to, you know, these 700, maybe you get 300 wrong out of 700. Okay, so your error rate is 300 over 700. There are different types of errors here as well. So this is a nuance that we'll start to think about and talk about a little bit more, especially as it relates to classification. Okay, let's say you really cared about getting the G movies correct. Okay. And maybe that's because, let's say, for example, all you had to go off of was the rating and the runtime. You really don't want to show a kid an R-rated movie, but you don't really mind that an adult would watch a G-rated movie, right? So you can actually tune this model to have a greater preference for getting the red part correct. And what that would do is that you would try and reduce your error rate related to red. So only in the red part, you're saying, okay, as long as my red predictions are correct, I'm happy. And you may actually increase the total error as an expense to try and reduce a particular type of error, okay? Right, you have the type 1 errors, type 2 errors, and you can actually kind of mess with the model in such a way that that you have a higher preference for a particular outcome. And that's going to get into some of the machine learning stuff that we'll do sort of at the end of the course. Okay. Any questions about this? Okay. So let me transition to talk about other classification examples. So we're going to look at two other examples of classification as alternatives to your multinomial logistic. So the first is known as a linear discriminant analysis, also known as LDA. So this is generally better for well-separated classes. If the predictors are normally distributed, it's more stable than logistic. And this is usually pretty popular when more than 2 response classes. Let me Okay, so I'm going to give some reference sort of math on how this works. But again, this is stuff that's kind of happening behind the scenes for when you actually run this function. It's not something that you'll need to memorize or anything. So we have Bayes' theorem, which maybe some of you might be familiar with if you've taken statistics courses. So this is probability of outcome K. And this is a density function of X for an observation from K. And the problem here is that we don't know what f of kx is. So we don't know that the density function of what x looks like for given the k observation. So LDA simplifies this by assuming f of kx equals 1 over square root 2 pi sigma times exp Okay, who can tell me what this is? Does this look familiar to anyone? No, no one's taken statistics. This is the definition of a normal distribution. And that's why when it makes this assumption, that's why this is kind of true. So your model tends to be more stable if the predictors are normally distributed because it's basically assuming that. So we've got this equation here, which is derived from this assumption. So this is kind of the punchline equation similar to the Logit equation that we have in a logistic regression. This represents assignments of observation to class K for which this term is the largest. So this is, again, analogous to our probability thing. So whatever outcome has this the highest is the one that gets sort of assigned. in the same way that we just did with the predict function that assign the highest probability into that sort of mapping. So the punchline here is that we are just presenting an alternative means of doing this kind of classification that we did with multinomial logistic, with certain characteristics that you can think about whether to do an LDA versus an MNL. Okay. And we will, okay, let's go ahead and kind of do this example really quick in basically the same way that we did for the multinomial logistic. So here, we're going to do example of linear discriminant analysis. And we'll be fitting the LDA model. Procedurally, this is going to be really close to MNL in all the stuff that we've kind of set up already. So instead of multinom, it'll be LDA, and it should look something like this. This has a bunch of information contained in the summary, and these things relate to sort of attributes here. Okay, so like your means for your Ks, it has some scaling that it has to do, and then the priors for your Bayes theorem. Okay, not something that you need to worry about too much. The interpretation of a lot of the sort of parameters here are not something that are really interpretable. We mainly care about the predictive outcomes from the LDA. Okay, so we mainly care about this thing. Oop. So here, we're going to do prediction using this, using the grid of values that we had created before, right? That was the Disney.new. So predicting across our range of vote ratings and movie length times using the LDA. And here, I am just going to straight up copy and paste this ggplot that I made before. And all I'm going to change is, whoa, wait, this is, what is this? Hang on. So I'm going to copy and paste this guy. And all I'm going to change is my new predicted ones where I'm going to do it from the LDA instead of the Logit. Okay, so run the predictions and then make the plot. And in this case, it'll look something like this. The predictions are relatively similar, but there are some, it'll be slightly different, okay? And so whether you use the multinomial logistic or the LDA, again, depends on the sort of context of the problem and where you think you might get sort of better. I mean, you could just run both and then calculate the error rates and see which one does better at predicting. Yes. Yeah, similar type of answer. This is not exactly the same, but they approach it sort of really differently. And in certain cases, like you might find that like one does substantially better than another. In this particular case, they probably have pretty similar error rates. Yeah. Do I have that explicitly calculated? Let me take a look here. If I click Disney.new, where are you? Is it this one? The way that you would calculate the error rate is that you would run this predict function against the original data. So let's do that. LDA.error. Predict. So okay, it'll be original would be what's it called? Disney.filtered dollar certificate, and then LDA dot predict would be equal to predict of our LDA fit. Nah. Okay, what's wrong with this? Okay, hang on. Uh-oh. Okay, oh, yeah. That's why. It is class. Yeah, okay. So in this particular prediction, it's giving a sort of different outcome. I believe it's giving me these values here, these delta Ks. And then if you do $class at the end of it, it will return the class that's the highest of my delta Ks. So it does the actual assignment. So $class. Okay, good. So what does this look like? I have my original and then the predicted value from the LDA. And all I have to say to calculate the error is I just count the number where these match. How would I go about doing that? It would be something like, okay, a rough way that you could do this is like n row LDA error where original equals LDA predict divided by n row of LDA error, I think. Or this would be the success rate, not the error rate. So it would be 1 minus that. What? Oh, sorry. No. Yeah. So you'd have an error rate of 59% here. In other words, right, 59% of the time you would guess wrong. Is that good or is that bad? We could calculate the MNL one too. So let's look at the MNL. It's the same, almost the exact same thing. MNL.predict equals predict. I think it was called MNL fit. And this time we don't need to do the class. So then 1 minus n row MNL.error with the original equals MNL.predict divide by n row MNL.error. Okay, they're pretty close. In this case, I might say that probably neither of these are going to be substantially better than the other. But what would a different baseline be? What would be, in theory, what would be the error rate if we guessed randomly? Yeah, exactly. So, okay, kind of. Let's suppose that you had an equal number of G, PG, R, and PG13. Then your error rate, if you were just to totally guess randomly, would be 75%. And so these models improve your ability to do prediction by what, 15, 16%-ish. Okay, so is that good? It depends, right, on sort of the context. And of course, it also depends on the sort of relative density of your different movies. Okay, so for example, like if 75% of the movies were rated PG-13, then I could just guess that they're all PG-13 and I'd probably have a better, error rate just because of the quantity of those movies. So there are some context that depends on sort of the setting of your data as well. Okay. Any questions about this? Okay, we are going to look at one more classification example. And this one, unlike LDA and MNL, is going to be pretty different. This is a totally non-parametric model. And maybe some of you guys have heard of this before. Okay. K nearest neighbors. Also known as K and N. Let me write the equation. Looks something like this. And again, this one is just for reference. I actually think this is one of the ones that's sort of easier to understand. Okay, so what's going on here? The sort of English description, given a positive integer k and test observation x0, identify the k points closest to XL, and this is represented by N naught. So this would be something like that. Estimates the probability for class J as the fraction of points in N naught whose response equals J. And then it classifies x0, x naught to class with largest probability. All right, what the heck does that mean? The explanation is actually rather simple. Consider something like this. Let's take some points. Actually, I'm gonna try and replicate this as close as possible. Here. Okay, so this is how K works. K nearest neighbors works. So let's say I have a map of these points of different outcomes, right? I have discrete outcomes, right? So this might be like G-rated movies and R-rated movies, something like that, right? And you have your different x's, x1, x2. Let's take a point right here. So the way this works is, let's say k equals 1. It's going to look at the nearest neighbor, just the first nearest neighbor. And let's say it's this guy here. So what should we assign this point, blue or red? Blue, great. Okay, now we have k equals 2. Now I'll have this point and this point. Those are my two closest neighbors. It's tied in this case, and it will then choose kind of the previous one, right? Technically the probabilities are equal, but I think a lot of the time the assignment just happens to whatever the previous one was for tiebreakers. 3 closest points. So this would be blue, blue, k equals 3. So now it'll look at the 3 closest points, which is going to be this one, and this one. So what would I assign this point? Red, right? There's 2 red and 1 blue. So this becomes red. Right, and so you can see, like, if you're sort of on the boundary, it might flip-flop between, depending on how many Ks, but if you're like out here, right, then all of your neighbors are going to be pretty similar. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. K equals 18. Okay, let's say I pick a point here and I'm doing k equals 18. What would this be assigned as? Red. And why? Exactly. Exactly. So the higher you get, the closer to the actual number of points, the more it'll just predict kind of the it will be overfit essentially. It will just pick the one that has the most quantity within your sort of data set. So at k equals 18, no matter where you pick, it's going to be red. So how do we decide what's the right number of Ks to use? What was that? The mean, what do you mean the mean value? I see. Well, the problem is if I do all the data points, right, you get this thing where now all of them just become one thing. And your predictions generally will be pretty good here, but like here, they're all going to be red. So you probably want something in between 1 and 18, right? Does anyone have any ideas how I might decide? Yes. Yes, exactly. That's exactly how you do it. This is cross-validation, right? That's exactly what we're doing. You basically want the one that gives you the lowest error rate possible. Okay, so you run across a bunch of different values to do that. Okay, so let's. Mm-hmm. Yeah. So you technically, well, so yes, but it's not that problematic to do because actually the functions will do it for you. So let's take a look at that. So here we're going to do an example of k nearest neighbors. And we're going to predict the cross range of runtimes and ratings using k and n. Whoa, what happened? There we go. I'm going to set this up in the same kind of way. Certificate.knn. Okay, and this function uses knn, and we're going to train on our data set here. And we're going to have a test set of the right, the expand grid, that matrix that we made for the new inputs. CL is essentially feeding the information to KNN of the class, the classifiers, or the not the your response variable classes. And in this case, I'm going to do three Ks. So I'm going to set K equal to 3. So it's just going to look at the 3 nearest neighbors. Yeah, okay, what happened here? Disney. Oh, thank you. I love getting errors when I'm doing it live. Okay. So here we are going to copy and paste that plot thing again. And again, all I'm going to change here is our KNN predictions. All right, so that plot there, that was our LDA, which looked really similar to our MNL. And so now let's take a look at what the KNN one looks like. What do you guys think? Is it going to be pretty similar? Okay. Whoa, all right. That is pretty different, right? So I can go in here and see whether these predictions kind of make sense, right? So I'm just gonna close my eyes and I'm just gonna, all right, this point right here, what are my 3 nearest neighbors? It's probably this guy is my closest. And then maybe it's either gonna be this and this, or it's gonna be this and this. it's probably these 3 points here are my closest. So there's 2 reds and a green. So I predict this point here is going to be red. Okay, so this works like really differently from what we were doing before. And I can use that same algorithm anywhere. I just plop my thing here. There are 2 reds and a blue. So this point's going to be red. Okay, that's how this gets filled out. It's someone waving a stick and no, but so you can also see that the like map of the predictions is highly nonlinear. Okay, this is like a very sort of non-parametric approach of doing this. And you end up with sort of maps that look like this. And I could, okay, so I don't actually have this pre-set up, but let me do the error rate really quick. The test would just be the same thing, I guess. Let me see. All right, we'll do one try at this. If not, this we'll pick. I'll look at it at home, and we'll pick this up next time. So data.table original equals Disney.filter $certificate, and our, what did I call it? Our KNN.predict is equal to this, and test will be the same thing. Oh, dang it. Accidentally hit Control-C instead of Control-V. So we'll copy that again. Okay, I think this will work. Parentheses at the end. Okay, sweet. Okay, that did work. So our error is 1 minus n row KNN error of original equals KNN.predict divided by n row of KNN error. Okay. So our KNN, even non-optimized, I just chose 3 randomly, has a 39% error compared to a 58% error. So in this case, it's doing a lot better. Maybe, right? This is all in sample training. So really probably what you'd want to do is do predictions out of sample. But yeah, hopefully you guys can see a pretty big difference between the MNL LDA approaches versus this non-parametric KNN approach. And I'll kick off next class. We'll wrap this part up. We'll look at ranges of different neighbors and seeing how to select them. Okay. Thanks, everyone. Homeworks are going to get posted today and due next week. I'll see you guys in 2 days.